Imagine sinking, just dropping past the sunlight, past the twilight zone, all the way down into the deepest, darkest crevices of our oceans. We're talking about a place so profoundly alien that, by all known laws of physics and biology, life down here shouldn't just be difficult, it should be absolutely physically impossible. We are talking about 11,000 meters down in the Hadal trenches. At this depth, the crushing hydrostatic weight creates an absolute physiological barrier of over 1,000 atmospheres of pressure. To put that into perspective for you, that is the exact equivalent of having a fully loaded commercial airplane resting entirely on your thumb. Everything we understand about basic biology says that cells should simply implode under that kind of weight. So, how do you survive when the entire ocean literally wants to flatten you into a titanium pancake? Well, it creates this massive biological paradox. These communities of extremophiles, specifically called barophiles, they don't just barely survive here. They fundamentally defy our standard terrestrial biological template. They actually rely on this crushing pressure just to exist. If you brought one up to the surface, it would die.
Chapter 1. The Ocean's Crushing Paradox.
Okay, let's really dive into how they pull off this magic trick, because we have to look at the mechanical impossibility of living under a water column that creates total molecular gridlock. Think about biological reactions, kind of like human breathing. Cells and proteins need physical space to expand and contract to do their jobs. In science, we call this volume change. But at extreme pressures, this is incredibly difficult. Imagine you're trying to shove open this really heavy, outward-swinging door. Now imagine a massive, densely packed crowd of people on the exact opposite side, pushing back with all their might. The biochemical volume change just requires way too much energy, and the whole system grinds to a total halt. The biological door just can't open. So if a normal cell gets pushed by that crowd, its membrane simply freezes into a solid, brittle block. It practically shatters. But to stop this from happening, these deep-sea organisms use an absolutely ingenious bioengineering trick called Homeoviscous Adaptation. They literally alter the chemical building blocks of their own outer skin so they can maintain fluidity. Let me break that down. Normal cell membranes use straight fatty acids, which pack really tightly together, sort of like straight metal pipes bundled up in the back of a truck. Under pressure, those straight pipes compress into an unbreakable solid. But our deep-sea barophiles, they use high concentrations of unsaturated fatty acids. These are like a collection of bent, crooked pipes. No matter how hard you squeeze them together, their awkward, kinked shapes mean they simply cannot pack tightly. This brilliant little microscopic geometry hack ensures the cell membrane remains supple, flexible, and most importantly, alive.
Chapter 2. Chemical Cages and Alien Engines.
So we've got the outer wall sorted. Now we have to move past that membrane and see how these creatures engineer their internal chemistry to keep their vital proteins from completely unraveling. To stop their cellular machinery from collapsing, these organisms quite literally inflate their cells from the inside out. They use these specialized chemical chaperones called Piezolytes, and the most famous of these is a little molecule called TMAO. Picture an intricately folded paper origami crane. This crane represents a highly delicate, absolutely essential enzyme inside the cell. Now, put that paper crane into an industrial hydraulic press. Under normal circumstances, bam, it's instantly crushed into a flat, meaningless wad of paper. But the magic of TMAO is that these molecules act like an invisible, rigid cage perfectly mapped right around that crane. When the immense weight comes down, this chemical cage reinforces the delicate folds, letting the enzyme retain its exact shape and function, even while being squeezed from every possible direction. But surviving the pressure is only half the battle, right? You still need energy, and you're in a world with absolutely zero sunlight. Up here on the surface, life's engine runs on sunlight and photosynthesis. It's like a standard car running on gasoline. But down in the pitch-black Hadal trenches, their energy metabolism is completely alien. It's like a car engine that somehow runs on its own soot and rest. They use a process called chemosynthesis, using specialized enzymes to strip electrons from toxic inorganic compounds, things like hydrogen sulfide and methane bubbling straight up from the Earth's mantle. They have literally built a thriving food web without a star to power it. Chapter 3. Sensory Survival in the Abyss. Zooming in even closer to the micro level, we find that these organisms don't just survive on a chemical level. They operate as highly redundant, finely tuned machines that are perfectly adapted to a silent, lightless void. Let's look at their actual biological code. Unlike surface animals that have to adapt to UV radiation, fluctuating heat, or changing seasons, Hadal genomes strip away absolutely everything unnecessary just to conserve energy. Their DNA is like a highly specialized library. All the random fiction and poetry sections are gone. This library is completely ruthlessly optimized for managing only the pressure-sensitive genes required to stay alive. Because think about it, in this extreme environment, if a cellular system breaks, you die. Instantly. To prevent this, their genomes feature an insane amount of gene duplications. It's exactly like a traveler driving through a desolate desert carrying 3 identical spare tires. If one set of protein folding machinery fails under the immense stress, it doesn't matter. A backup biological construction crew seamlessly takes over. They have evolved these built-in continuous fail-safes to ensure vital biological construction literally never stops. And how do they interact with their environment when they don't have eyes? Navigating the abyss requires sensory apparatuses that act like high-gain radio antennas. Surface animals navigate like reading a book by a lamp, but Hadal organisms navigate like reading Braille in a pitch-black room. They use incredibly refined touch, chemosensory cues, and vibration to perfectly map the topography around them. They can literally feel the tiny water displacement of a single crustacean moving dozens of meters away. But they also have to be patient. Because the abyss is essentially a nutrient-poor desert, they operate on what biologists call a slowed metabolic clock. Think of it like a high-efficiency battery that simply refuses to draw power unless it is absolutely necessary to survive. By drastically lowering their resting heart rates and deliberately slowing their metabolic throughput, they stretch their lifespans out just waiting quietly in the dark for months for their next meal to drift down from above. Chapter 4. The Blueprint for Alien Life. Let's zoom out to the macro implications, because the physical structure of these creatures is way more than just a biological curiosity. It actually provides the ultimate blueprint for astrobiology and human biomimetics. Look at their armor. In the deep ocean, calcium carbonate, the stuff normal shells are made of, usually just dissolves. Yet these organisms maintain rock-hard exoskeletons through a process called mineralization. If you look at a microscopic cross-section of a Hadal shrimp shell, it isn't solid bone. It's structured exactly like a reinforced concrete bridge. They strategically include magnesium and phosphate ions that act as structural rebar within the shell matrix. It is designed with just enough give and flexibility to absorb the ocean's crushing energy rather than shattering against it. Honestly, this completely flips our slightly arrogant understanding of environmental stress. We build all our scientific frameworks around one-atmosphere organisms, like us. To a human, 10,000 meters down is this insurmountable lethal limit. But we tend to forget that to a hadobacterium, that's home. And our surface world of gentle breezes and sunshine, to them, that's a terrifying, lethal vacuum of low pressure. The implications here for our future are absolutely staggering. The resilience of these barophiles actually provides a roadmap for extremophile engineering. We can learn from them to synthesize artificial proteins for deep crust carbon sequestration or entirely new industrial manufacturing. But way more importantly, if life can colonize the Mariana Trench using these biomechanical tricks, it exponentially increases the likelihood of finding equivalent life in the subsurface pressurized oceans of icy moons like Jupiter's Europa or Saturn's Enceladus. This means we've got to stop looking at extreme pressure as a barrier. We really must consider the barophilic model as the new standard template for resilient life. These organisms are teaching us right now how to build deep-sea autonomous sensors and future interstellar technologies that won't shatter under pressure, but will actually use that pressure as a foundation for performance. So as we map the metabolic limits of these deep-sea extremophiles, we start to realize we aren't just looking at weird fish. We're looking at alien technology already thriving right here on Earth. And that leaves us with one pretty staggering question to ponder as we wrap up this explainer. If life not only survives, but thrives in places where it should be physically impossible on our own planet, what exactly is waiting for us in the dark oceans of other worlds?